All right, in this explainer, we're going to pull back the curtain on something that might feel like a secret code, but it's actually the language we use to organize, well, pretty much everything. We're talking about set theory.
Okay, let's just dive right in. You see these symbols on the screen? A pair of curly braces, a kind of upside-down U, that weird-looking E? What on earth could possibly connect all of them? They might look totally random, but trust me, they're all part of one beautifully simple system for making sense of the world.
You got it. They're all part of the language of sets, and it's an incredibly powerful way to group things, sort them, and really understand the relationships between collections of, well, anything, from numbers to people to ideas, you name it. So to really learn this language, we've got to start with the most basic building block of all, the set itself. So what exactly is a set anyway? Honestly, it's about as simple as it gets. A set is just a collection of distinct things. We call those things elements, and we always write them inside these curly braces. That's it. That is the absolute core idea. Now, to keep things consistent, sets have two golden rules you gotta know. First up, order does not matter. The set with A, B, and C is the exact same set as the one with C, B, and A. And second, no repeats. An element is either in the set or it isn't, period. You can't have it in there twice. The set just ignores any duplicates, which, fun fact, is a core reason why databases can handle unique info so darn efficiently. Okay, so how do we say if something's actually in a set? We use these cool little symbols. This one that looks like an E, that just means is an element of. So here, 2 is an element of the set containing 1, 2, and 3. And if you see the same symbol with a slash through it, you guessed it, it means is not an element of. Simple, right? Okay, now that we know what a set is, we can start to have some real fun. Let's dig into the blueprint for how we can describe sets with precision and, more importantly, see how they relate to each other.
Turns out there's more than one way to define a set. You could just use plain old words, nice and simple, or you can list the elements out directly. That's called the roster method. And then there's this one, set builder notation. I know, it looks a little intense, but it's just a super precise rule. You read it like this: the set of all elements x such that x is a natural number and x is greater than or equal to 5. The cool part? All three of these describe the exact same set.
Now hold on, before we start comparing sets, we need to set the stage. We have to define our universe. The universal set, or U, contains every single possible element we're considering for whatever problem we're working on. It's the big sandbox that all of our other little sets get to play in.
Once we have our universe, we can talk about subsets. It's a really simple idea. A set B is a subset of set A if every single thing in B is also in A. Think about it like this. Your 90s rock playlist is a subset of all the music on your phone, right? Every song on that playlist is also in your main library. Now here's a tiny detail, but it's an important one. The regular subset symbol, the one with the little line under it, means that B could be completely identical to A. But if you see this symbol without the line, that's a proper subset. That's a stricter rule. It means B absolutely must be smaller than A. It can't contain all the same elements. So what happens if a set has, well, nothing in it? Is that even allowed? Oh, yes. It's called the empty set, and you can write it as a 0 with a slash through it, or just a pair of empty curly braces. It's a totally valid set, and it has a cool property. It's technically a subset of every other set out there. And that leads to something kind of mind-blowing. Let's say you have a tiny set with just 3 things in it, like A, B, C. How many different subsets could you possibly make? The answer is 8. You got the empty set, the little 1-element sets, the 2-element sets, and of course the whole set itself. And it's not random, there's a formula. 2 to the power of n, where n is how many elements you have. You can see how quickly the complexity can grow from just a few simple rules. Okay, this is where theory becomes a tool. Knowing what sets are is cool, but the real power comes from what you can do with them. So let's look at the operations that let us combine, compare, and mess around with sets. First up, the union. The symbol looks like a U, which is perfect, right? U for union. Taking the union of A and B just means you're creating a new, bigger set that has everything from A and everything from B all thrown together. You're just merging your collections. Next is the intersection. Now, instead of combining everything, the intersection gives you only the elements that the two sets share. It's that common ground, the specific stuff that's in both A and B. The difference is pretty much just set subtraction. If you see A\B, it means start with all the stuff in set A and then take out anything that's also in set B. What you're left with are only the elements that are unique to A.
And finally, we have the complement. Remember that big universal set we talked about? The complement of A, which we write as A prime, is every single element in that entire universe that is not in set A. It's literally everything else on the outside. Okay, I know that was a whirlwind tour of new terms and a ton of symbols. So to make sure it all sticks, let's wrap this up with a super handy visual guide that puts everything we just learned in one spot.
This right here is the perfect slide to pause and screenshot. Think of it as your personal glossary for the language of sets. We've got pretty much everything we covered, from the basic element of symbol all the way to unions, intersections, and complements. You might even spot one we didn't cover, the Cartesian product, which is a more advanced way to create ordered pairs. A little something to look into next.
So why does any of this really matter? Because this isn't just a random chapter in a math textbook. Set theory is the actual blueprint for how databases work, how computers figure out what you're searching for, and how we build solid arguments and logic. It's a fundamental tool for just thinking clearly. And that leaves us with a pretty powerful thought to chew on. This whole language is about drawing lines and defining what belongs. So the next time you come across a category, whether it's in data, in an argument, or just in everyday life, ask yourself, what are the rules of this particular set? And maybe more importantly, who gets to decide what's in and what's left out? It's a question that can really change how you see the world.